Okay, hello everyone. So in this tutorial we will do some examples related to capacitor problems, capacitors in um, capacitors in mainly in DC circuits, but maybe we will see some examples related to some functions circuits. Okay, uh, we will start with a warming up problem, a very simple problem, direct related to the direct relation of the capacitance and the charge. So you connect a capacitor of 3 microfarad to a voltage source and 12 millicoulombs of charge accumulates. The question is how much is that voltage source and how much energy that voltage source stored on the capacitor, or how much energy it spent to store this amount of charge on that capacitor. In other words, uh, we have we have a capacitor and we connect that capacitor to a voltage source. Then the capacitor is 3 microfarad. The amount of charge that accumulated is 0.12 millicoulomb. How much is the voltage source? This is a direct relationship, or there is a direct relationship between capacitance, the accumulated charge, and the voltage applied on the capacitor. And V hence equals Q over C, that equals, or that gives us V equal 0.12 millicoulombs over 3 microfarads with some math and exponential 10 to minus 6, 10 to minus 3, and so on. We get 40 volts. Okay, so the battery was 40 volts, and that battery spent some energy to accumulate this amount of charge here. So how much that energy that the battery stored on the capacitor? Well, we know that the battery, or the work, or the energy, equals half CV square. Again, this is a direct relationship, so half 0. Oh, sorry, this is the capacitance, so it is 3 times 10 to minus 6 times 40 square. If we do the calculations, we get 2.4 millijoules. So this is the amount of energy this battery spent to store this amount of charge on this capacitor. Okay, so this is a warming up problem. Let's see another one. In this problem, we have a capacitor of 10 microfarads connected to a variable source, and we are asked to find the current that goes through the capacitor. Now, to elaborate a little bit on this problem, we know that a resistance from Ohm's law is related to its voltage and the current in the resistance IR. This is R, and the voltage of the resistance, they are related linearly. So IR, the current, equals VR over R. This is Ohm's law, and it is the typical relationship. In case of a capacitor, the voltage across the capacitor, VC, and the current through the capacitor are related in a different way. They are not related linearly like Ohm's law. Rather, the current of the capacitor equals C, the derivative of the voltage across the capacitance with respect to time. So as long as there is a change in this voltage, if this voltage across the capacitor changes, there is a change here, then there is a current. But if this voltage does not change, then there is no current and the capacitor behaves as an open circuit. Having said that, it is now clear that we can find I of C, the current of that capacitor, equals 10 times 10 to minus 6, because it is in microfarad, multiplied by the derivative of VC with respect to time. and that equals, so IC equal 10 times 10 to minus 6 times 50 sine 2000 t prime. Now the derivative of 50 sine 2000 is actually 52,000 cosine 2000 t. When we do that multiplication, this 50, this 2000, and this 10 with this, we end up with 1. So it is 10 times 10 to minus 6 times 50 times 2000 times cosine 2000 t amperes, and this equals cosine 2000 t amperes. Okay, that's it for this problem. Let's see another one. So in this problem we are asked to find the total capacitance or the equivalent capacitance seen by this terminal, by the terminals A and B, these ones. Now capacitances, they behave opposite way of resistances in terms of connection. So when they are connected in series like these two, the relationship that holds is that the reciprocal of the total equal the summation of the reciprocals of those capacitances, or like resistances in parallel. So the total of these two, 5 times 20 over 25, and that equals 4. So now our capacitance circuit looks like this. We have a 4, we have a 6, that's this one, then we have a 20, and finally we have this 60. Now capacitances in parallel, they add up. So these guys add up. We have 4 calculated, 6 and 20. The total is 30. So we have one capacitor 30, one capacitor 60. They are now in series between the two terminals. Capacitances in series, they behave like resistances in parallel. So 30 times 60 over 90, their total, and the answer is 20 microfarad. Don't forget the micros and millis in capacitances. Okay, to our next example. Okay, in this problem we have a group of capacitances connected to a source, as we can see, and we are asked to find the total voltage or the amount of voltage on each of these sources, of these capacitances. Okay, so here it is. Now one way to deal with this is actually to find to reduce the circuit a little bit. So these two capacitors are connected in series. Their total is actually like resistances in parallel, so it is less than the smallest one, and if we do that, we get that both of them are together in series give us one capacitor of 20 microfarad connected in parallel to this one, which is 20 microfarad. Then we have here 40 microfarad, and we have 60 volts. Now the 20 microfarad and 20 microfarad in parallel, they add up. So we have now one source of 60 volts and one capacitor of 40 microfarad and one equivalent capacitor of 40 microfarad. 40 microfarad, 40 microfarad. So since both of these capacitors are the same, then this voltage source, the 60, is going to be split equally on these two. So that means by default this guy has 30 volts now, because it gets half of this 60. Okay, and so we have 30 volts here and we have 30 volts here. Between this one and this one there is 30 volts. So if we redraw this, we actually have now one capacitor here of 20 microfarads, that is this guy, with 30 volts across it, and there is one capacitor of 60 and one capacitor of 30, and so this guy has 30 volts across it, and both of these two, because they are connected in a parallel connection to this, they have 30. So now how do we split 30 volts on two capacitors? One of them is 60 microfarads and the other one is 30 microfarads. Okay, and they have 30 volts together. How does this 30 volts split on these two? Well, since capacitance is, I mean, one way to think of this is to think in terms of resistances. Capacitances behave opposite way of resistances when it is related to connection. That is, if this was a resistance series connection, we know that the bigger resistance will take the bigger chunk of the voltage, because it is the same current passes in both. Current times resistance equals voltage, so that's why the bigger resistance gets bigger amount of voltage. In the capacitances it is the opposite, so since it is the same current that passes through both, okay, and we know that voltage equal Q over C, so Q is actually the current. Current is just charge moving. If same current passes through both capacitances and one of them is less than the other, that means the voltage on the smaller is going to be bigger than the voltage on the bigger, because the current is same. Hence we expect that the voltage on this one to be 20 and the voltage on this one to be 10. If you like, you can do the following as well. Another way to be safe without thinking too much, actually calculate the total capacitance, which we did, and it is 20. Find the Q, find the charge Q, and then that charge is going to be on this capacitor and in this capacitor. Divide that charge by this capacitor and this capacitor and you get the same answer. So to answer the question, this guy has 20 volts across it, this guy has 10 volts across it, this guy has 30 volts across it, and this guy has 30 volts across it. Let's do another example. Okay, in this example we are asked to find the energy stored in each capacitor. So we have two capacitors, we have this 2 millifarads and this one 4 millifarads capacitors, and we are asked to find the energy stored in each one. So this is a source, a current source. It gives current away, and this capacitor will accumulate some charge, and this capacitor will accumulate some charge, and that actually charge, capacitance, voltage gives us energy. Okay, now one of the important things that we need to understand, that in DC analysis of capacitors, after the steady state has passed, the capacitor behaves as an open circuit. So when we switch on this circuit, switch on, then capacitors charge, we have the charging process is a transient process. When it stops, the capacitor is actually an open circuit, behaves as an open circuit. Capacitor behaves like open circuit. Okay, now this is the assumption, of course, that this circuit reached steady state and the capacitor is now as an open circuit. Then our circuit becomes something like this: a resistor here, 2 millifarad, 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 2 a resistor here but without any function because there is an open circuit of the capacitor, a resistor here, and a resistor here, and the capacitor connected here, which is an open circuit. Sorry, an open circuit. So since we know the capacitance of each of these, we can, if we know the voltage across them, we know the energy stored. So what we need now actually is to find the voltage across this resistance because it is in parallel with this capacitor. That means we will get the voltage across the capacitor and the voltage of this resistance. Again, it is in parallel with this branch, and in this branch only the capacitor has voltage drop because the resistance says voltage drop is 0 as there is no current here. The capacitor is an open circuit. So this is 2 kilo ohms, this is 4 kilo ohms, and this guy is 3 kilo ohms, and this one is 6 milliamps. Now we can use, for instance, nodal analysis. Put a node here, find this current, find this current. You can do many things if you want, but there is an easy way to do this. These two guys, these two resistances, the 2 and the 4, are connected in series in this connection, as there is no current here, no current here, so they are together in series. Their total is 6 kilo ohms, and this one is 3 kilo ohms. So the current here is half the current here. The current in this, actually in this one, is double the current in this one, because the resistance is double. In other words, if you imagine, we have 2 kilo ohms, 4 kilo ohms, we have 3 kilo ohms, and we have a source of 6 milliamps. So the current in this branch is going to be half the current of this branch because the resistance here is double the resistance here. End of the story. So the current here is 2 milliamps and the current here is 4 milliamps. Okay, so 2 milliamps. Now I have to make some cleanup. So if we agreed, maybe I can, oops, sorry. Okay, so if we agreed that the current here is the current here is 2 milliamps and here is 2 milliamps because it is the same current, while the current here is 4 milliamps, we can find the voltage here. The voltage here is 2 milliamps times 2 kilo ohms, that equals 4 volts, while the voltage on this resistance is 2 milliamps times 4 kilo ohms equals 8 volts. So this capacitor has across it 8 volts and this capacitor has across it 4 volts. The energy stored in this one equal half the capacitance, 2 times 10 to power 3 minus 3 times 16, which is the voltage square, and that equals 16 millijoule, because this guy and this guy leave, 16 millijoule. For this one, half the capacitance, which is 4 times 10 to minus 3 times 64, it equals to 128 millijoules. This is the amount of energy stored on this capacitor. Okay, so this is a group of problems related to capacitors. In another set we will talk a little bit about charging time, discharging time, and how we solve problems when we switch on off circuits with capacitors. Thank you for watching and see you in other examples.